Okay, thanks. Okay, I have to thank for the invitation and to thanks all of you people here because they will suffer to my talk. So what I will talk is about some. It's a problem that is related to some old stuff. So first of all, I will give a short introduction to the problem and see which are the development in this topic. I should say that this is a joint work with lots of people. So Francesco Dalla Piazza, Alessio Fiorentino, Sam Gruszewski, and Sara Perna. First of all, just a comment about, there will be in a few days, I think, will appear something on archive. I mean, there is a first version. And a general recommendation to the audience. If you write a paper in 5, democracy does not work at all. If you start to discuss which is the best form, then you never finish. But this is just, now let's talk about mathematics. So, first of all, I fix some notation. So, Hg, as already somebody introduces, to me is the Ziegler space, so the set of G by G matrices, complex matrices, such that the tau is symmetric and the imaginary part of tau is bigger than 0. As Giulio said, yes, this is the obvious generalization of a Ziegler of the upper half plane. So this is called Ziegler upper half plane. So obviously everything that I will say is over C. So a theta function a priori, I don't want to give a precise definition, is a holomorphic function on Hg cross Cg, and usually one can write theta of tau z, something like this, that has a certain transformation formula that I will explain later, I will recall later, but that it's more important, at least for me at this moment, that it satisfies the heat equation. This means essentially 1 plus delta ij, let's write this way, divided by 2 of delta of d tau ij. This is the derivative with respect to the element of the symmetric matrices of theta of tau z is equal to 1 over 4 pi I, or the second derivative of theta with respect to zi and zj of tau z. So I define the differential operator, the matrix differential operator, then delta is equal just the one here. So 1 plus delta ij divided by 2 of d tau ij. And I want to study an object of this type. So I want to consider a matrix A. So, equal to, let's say, h square of delta of f over g, f over h, sorry, where f and h are theta functions, are different theta functions, obviously, theta functions, evaluated at z equal to 0. So why do I want to consider this? So to this very simple form, then I will give you an example of this. We can give you an example of this form with theta constant. I associate two results. I will state two results. No, this is a matrix operator. It's a matrix operator. So this is G by G symmetric matrices. So if you want, maybe it's better, right? So Aij is equal to h, I mean, this h square, I forgot the h square. Now, okay, let's d over d tau ij of f times h minus the f d over d tau ij h, and then here I have to write 1 plus delta ij divided by 2. I didn't want to write because it's going to be rather heavy, the notation. But the statement is very easy. So the two results. First of all, so two results. One is a simple remark, but there's could have some further development. Let's consider the matrix, the symmetric matrix, the matrix A added, so the adjoint of the matrix A. So the matrix was entries are the G minus 1 times G minus 1 minors of the matrix A. And let d tau ij check is just the wedge product. Let me write this. I mean, for physicists, this notation would be nice, but for mathematicians, less. But the wedge product of d tau hk over h less than, okay, h less or equal than k less or equal than 1 less or equal than g divided by d tau ij. So the wedge product of all differential except tau ij. And then I define this formula, omega is equal to the trace of the adjoint, A adjoint, d tau ij check. This result, this formula here is a holomorphic differential form of degree 1/2 g times g plus 1 minus 1. This is the top degree, so minus 1 minus the top degree on hg mod gamma, where gamma is a suitable subgroup of finite index. Gamma is contained in gamma g that is equal to sp to gz. So Oh, unfortunately, I cannot use this form to improve result about the general type. I mean, all the results about the general type are already known in the sense that the only result that in which we are really interested that in genus 6, if so if it is A6, that is just A6 divided by gamma 6, if this is unirational or not, if it's general type or not. This still I do not know. But this form, homomorphic differential form will be nice because it's a kind of bridge. Then I will, if I have time, I will show that this is a bridge between two different constructions. One made by Freytag. It was 40 years ago. Another one that I did 30 years ago. And I should say that the Freytag construction is the first construction for which essentially has been proved that modular variety, they were not unirational, but I mean, then obviously there's been result by Mumford et al. About the possibility to extend the section of the pluricanonical sheaf to the boundary and so on. I mean, no. In this case, there is a theorem due to Freytag, Pomerening von Cotto. It extends. I mean, for all the holomorphic differential form except the canonical form and the pluricanonical form, they extend. So, but this form also used for this form also will be the main tool in showing the following result. Principally polarized Abelian variety that I will write at the moment x tau theta tau, then I will try to define everything, is decompensable so essentially it's a product if only if the image via Gaussian map of all smooth point of order 2 in theta of tau is contained, the image is contained in a quadric. Q. So one implication of this fact is it's obvious. I mean, if it's compensable, even all the Gaussian map is contained in the quadric. But in this case, I just reduce the vice versa to consider only point of order 2. And this is something like a theorem that could be related to, what can I say, Mumford theory of Abelian variety, for which essentially you know the equation of the Abelian variety once you know the image of a point of order 2. We have the map, Lefschetz map, or also, for example, completely different topic, but not so different. I mean, obviously completely different way. What Caporas and Cernesi proved about bitangents of so the bitangents in this case will relate it to point of order 2, but just this is for modular space of curves, and the injectivity of the Gauss map when it's defined on the period matrix using the Gauss map. So this is so to do this I have to recall, I'm sorry, some basic fact. So essentially, since here theta function is a theta function in two variables, tau and z, I have to record some basic fact about Abelian variety and some basic fact about the modular forms. So first of all, I will try to be fast. a vector whose entry are 0 and 1 in the 2G vector. And for my convenience, usually write M as M prime and double prime. At this point, I define a theta function of characteristic M is equal to, I can write this as also theta M prime and double prime of tau z. This is equal to the summation of a P that belongs to ZG, the exponential of pi I of a transpose of P plus M prime over 2 tau P plus M prime over 2 plus transpose of P plus M prime over 2 zeta plus M double prime over 2. M prime appear 3 times, M double prime 1 time. Usually it's a mistake. No, it's correct. Oh, this theta function, some property. One, they are solution of each equation. Two, let's say, theta 0, 0 of tau z is called use a Riemann theta function. This is an element. This is essentially the unique section of unique up to scalar, obvious, x tau of L, where L is the principal polarization. Where here x tau is just a CG mod 1G tau. This lattice. Sorry. Tau 1G. And usually this can be written as okay. And this is line bundle L is the line bundle given the principal polarization up to translation, and it is a symmetric line bundle, but as a symmetric line bundle, it's not unique. I mean, if I consider any translation for a point of order 2, so we have that theta M of tau z is a section in the H0 of x tau of this tau. Let me write M always here. M, I consider M as a characteristics, or I consider M as a point in x2. Point of M, in this case, is equal tau M prime plus over 2 plus M double prime over 2. And essentially, this tells us that if we consider the Riemann theta function and then we evaluate it at the point M, it's something like to take this Riemann theta function and consider it at zeta equal to 0. It's not really the same, but it's equal up to a proportional factor. And also, this is true also for derivative. So, evaluation of theta 0, 0 tau z and derivative at M is equal to tau M prime over 2 plus M double prime over 2. This is equivalent to evaluation of theta M tau z and its derivative to zeta equal to 0. So another thing that I have to recall that there will be mostly my tools. I mean, something that is really classical. So if you want to choose a symmetric line bundle here, lam L or any of these translated is OK. So in some sense, if you want to consider the theory of Abelian variety, L is, I mean, more than L, or even if you have a principal polarization, more than L is the intrinsic L square. So if you consider the line bundle L tensor 2, this is equal. This is by a, and essentially what from this observation, this follows the first stupid but fruitful observation. If I consider the section of this line bundle, this is a 2G dimensional space, and the basis is given by theta functions, let me call it this way, theta of theta, capital theta, sorry, epsilon of tau z that are by definition equal to theta epsilon 0 to tau to z. I will prefer use this notation for this. Now, since this line boundary is this, one thing one have is easily that a set of generator of this space is given also by the theta m tau z square generators. And we have something that if Giulio said that is old, this is really old because it's, this is 100 years, even 150 years old. So I was not there. So we have one way to express theta m tau z square is equal to the summation. I want to write this as plus or minus theta sigma plus m prime of tau z theta of sigma of tau 0. A summation of a sigma that belongs to 0, 1 to the g. So, last remark about theta function, that is, everything is very classical, what I say, is the following. If you consider this theta function, they give a map, capital theta, that goes from x tau to p to the 2g minus 1, in such a way that the image here, so this map factorized over plus or minus 1, and the image here is just the Kummer variety. I mean, this is the image. Is the Kummer variety. If only if x tau, theta of tau, at this point I use the notation theta of tau for L, for the line bundle, is indecomposable. If this splits as a product, then this map is not anymore an embedding. As a consequence of this fact, to be an embedding, this can be translated in the following fact. If you consider the matrix M tau, I mean, this is important than what happens in the point of order 2. So if you consider the matrix M tau, that is equal to theta epsilon tau 0. So all the 2 to the g theta functions, and you consider the derivative of theta epsilon of tau 0 of the So for my convenience, I use the derivative with respect to tau ej. But here it is considered as a map with the period matrix fixed. I have to consider as a map in which the variable is z. But the derivative with respect to zi, zj is equivalent to consider this derivative. So this matrix has maximum rank. If only if this is indecomposable. Otherwise, the rank drop down. Now, let me recall something about what? Why? Which is true. I want which one? Why is true? This on this?
No. If m of tau is
as maximum rank. But essentially, if you want morally, to have this matrix maximum rank means that this quotient, when you consider in 0, is an embedding. What? Yes, in 0, and since everything is in 2 tau to z, in all point of order 2, it's the same thing. I mean, it's the same problem for all point of order 2, that are the singular point. What? This was the crucial point. I mean, you have to go to check it's an embedding, and then you have you have a Jacobian criterion for smooth point. I mean, you consider derivative. If you consider where you have a singular point, then you have to consider a second derivative with respect to zi, zj. That means to consider the derivative with respect to ij. Okay, now. Just because we want to talk about modular variety and so on, I have to just tell you that theta m tau 0 and theta epsilon tau 0, and from now on, in this case, I will omit the 0, are modular form, are scalar valued. Modular form of weight 1/2. What does this mean, essentially? Okay, just shortly. Siegel modular forms. It is known that SP2G R acts on HG for such a way that this is a homogeneous space to HG. And the action is that they use the standard action ABCD, and the point tau go to A tau plus B times C tau plus D to the minus 1. I consider gamma a subgroup, discrete subgroup containing, let's say, considering gamma G, it's a finite index, and V rho, and irreducible representation of GLGC. So I want to consider holomorphic form defined on HG with the value in V rho. that has some transformation formula. So, since an irreducible representation of a GLG is known when is known is highest weight. So essentially we can say that rho, we can associate rho a GUPLA of Lewis L1, L2, LG that belongs to ZG. This is highest weight. And essentially, I want to consider holomorphic function f from Hg to V rho, such that f of gamma tau is equal to rho of C tau plus D times f of tau. This is for every gamma that belongs to gamma contained in gamma G. This condition is enough when the G is bigger or equal than 2. When the G is equal to 1, I have to require some... what? For GLG, the irreducible representation. This is G by G invertible matrices. Here, the highest weight I consider with the integral. Obviously, usually, they should be positive integer, but also I require, and this can be done, I don't want to explain, that also half integral. In the sense that this is the representation. Here you can multiply by the determinant of C tau plus D to the 1/2, something like this. But, so by abuse or language and notation, I use this half integral. That's much easier to understand. So the scalar case is lambda 1 is equal to lambda 2 is equal lambda G, okay, is equal K, and this is called the weight of the modular form. As I said before, these two are modular form weight 1/2. Now, but to give some more example, for this theta, I did not tell you that if you consider these theta functions, these are even theta functions, always even theta function in the variable z. So you can evaluate that zeta equal to 0, it's okay. There are some that are even and some that are odd. So the odd theta function, when you consider at zeta equal to 0, this is identical equal to 0 as a function, so it does not have a, but you know, in any case, but the even case is good. So I can, but at the same time, now I can consider this a new modular form. I can consider Vm of tau is just the gradient of an odd theta function, so m odd. Sorry. To be odd or to be even, m, so I write E of m is equal to the transpose of m prime times Abel double prime. And this can be essentially even or odd. So the theta function will be even if the scalar product is even, if the function will be odd if the scalar product is odd. So for example, when G is equal 1, there are 3 even and 1 odd theta function. When the G is 2, there are 10 even and 1 and 6 odd. These 10 even are those that just Ma was telling before. The product is Igusa Chi5. So suppose that M is odd. Then this is a standard. Take the derivative, it becomes an even function. You can evaluate z equal to 0. And then I can consider the gradient with respect to z equal to 0 of the theta tau, and then of z. OK. And this is what can be proved, that this is a vector valued modular form with eigenweight vector is 3/2, 1/2, 1/2. So this essentially means that rho is just the determinant to the 1/2 times the standard representation of GLG. The standard representation is, is 1, 0, 0, 0. So this is another example of vector value modular form with respect to a certain group gamma that I will prefer not give a description. At the same time, if we consider Vm as a column vector of tau, the transpose of Vm of tau, this is same vector value modular form. Of eigenweight 3, 1, 1, 1. Something like this. Now, the nice result is the following, that Sam and I proved 10 years, yes, a little bit more than 10 years ago. Using the same notation. Sorry, I did not. So before, at the beginning, I defined a matrix A. So I want to define A epsilon delta. This is just equal to theta epsilon square. The d of theta delta divided by theta epsilon. Obviously, this is a scalar value modular form that multiplies something that is a vector value modular form. So everything is a vector value modular form. And the representation is the same of this. But what can be proved is the following proposition. This was Gruszewski and myself. It was 2002, 2003, something like that. That the space spanned by the Vm transpose Vm and the space spanned by the A epsilon delta is the same space. And this is essentially is a consequence of the formula that I erased that was here, that was the so-called Riemann addition formula, the one that was really old. So you can differentiate appropriately that formula, you get this form. And now I want to use this fact. And we have an explicit expression for which each term here can be expressed as a linear combination of terms here. And remember that these are matrix variables. And here M is odd characteristics, and here epsilon and delta are in 0, 1, G. It is odd in 0, 1, 2G. So it seems Now, let me try to prove the second theorem, and the theorem about the Gauss map. Yes, it's not obvious that they are linearly independent. No, they're not. I'm sure that they are not linearly independent. But the space is the same. You can down. Really, we never studied if there was. Sorry, one thing about the Gauss map. So we have a Abelian variety x tau, theta tau. So theta is the divisor, and we have a map G. It's going from the smooth part of theta to Pg minus 1. I take a point x here and associate just what I call, such that this is tau. I can define this way, Wu V0 of tau of x. So the gradient of the theta functions evaluated at the point x, that is a smooth point of the theta. What is known? G is dominant if only if x tau, theta tau is indecomposable. And is this known that instead, if, for example, if tau has this form, tau 1, 0, 0, tau 2, or is this gamma G conjugate to this form, then it's easy to check, since you have this form, what happens for the theta function. If you have a theta function, the classical theta function of tau z, become the product of theta function of tau 1 z1 times theta 0 of tau 2 z2. And if a point x is here, x is equal x1 or x2. But this means or x1 is in the theta divisor of the first block, or x2 is the theta divisor of the second block. So what happens if you take this function, you consider the derivative, and you evaluate at this value, x1, x2, depends which one, x1, x2 is in the block theta 1 or theta 2. Essentially, that the map, if you consider v of tau over x, is a vector like this, and all 0, or a vector like this, 0, 0, 0, star, star, star. Okay? Now, what is going to say? So this depends from the splitting, but in general, this means essentially that the image, in this case, of G is contained in a quadric contained in Pg minus 1. Really, not only in one quadric, but in many quadrics. So all quadrics of type xi times xj equal to 0, where I runs between the first, let's say, k coordinates, and j runs between k plus 1 and g. This is k. Okay? So this is the image of the Gauss. So this is clear. This is simple. So I want to prove the converse. I want to prove the converse in a different. Yes, the dimension of the image is is just one less. It depends from number of blocks. So it's G minus number of blocks. So if it's irreducible, it's G minus 1. If it's G minus 2, so. Yeah, this is 2 blocks. You can get more blocks. Also, one remark, if, this was, sorry, put 0, if x is in theta smooth a point of order 2, instead of considering nu0 tau evaluated x, I mean, this is equal to tau m prime over 2 plus m double prime over 2, I can consider nu m of tau evaluated at 0. This is the same thing. All of them, right? There are many quadrics. No, so sorry, maybe yes, I did something wrong. No, the dimension is much smaller. Yes, it's smaller. It's smaller. Yes, sorry. I mean, from this you can get the dimensions. Yes, the dimension is okay. In one side is contained in this hyperplane. The other one is so the biggest between these two. The dimension. So it's the maximum between k and g minus k. You want to know the dimension of the image. The maximum between k and g minus k. Well, k and g minus k. No. Sorry.
This means that it's contained in a very small linear space.
Yes. No. But this is for this special case. But if you act, then it's the same. And this, in fact, brings you to its characterization. So essentially, taking, if this point is a smooth point here of order 2, this is equivalent to say that this implies that the characteristic M is odd, necessarily, because if the characteristic was even, then if the point is there, it's automatically a singular point. So at this point, I have this situation. I have this function, Vm, M odd, and Vm of tau. This is a modular form. To check that this condition, I mean, does not depend from this decomposition, because a point, this is a point, reducible point, but the definition of a reducible point is a point tau such that gamma tau is equal to tau 1, 0, 0, tau 2, where gamma belongs to the symplectic group, integral symplectic group. So I should prove something similar for all these possible tau. But since this is a modular form, the transformation formula for this modular form that was using with respect to this representation is just a factor of the determinant times the standard representation. When I consider this, this condition does not change. I mean, this condition to be in a subspace is always contained in this subspace and this subspace. The equation of the quadratic changes, but it's always contained in a quadric. So this never changes. So what can I say? That V of M of tau, in any case, is contained in a quadric. Because applying the transformation formula, just doing a transformation through GLN. So if some point is in a quadric, it's transformed is in a quadric. So all these points are in a quadric, they are contained in a quadric. Okay? Now, I want to prove the vice versa. Okay, to prove, assume that V of M of tau belongs to a certain quadric contained in PG minus 1. I can say for all M odd characteristics without any loss of generality. Then I want to prove that, then I would like to prove that x tau, theta tau, is reducible, is decomposable. Okay. Now, since this is contained in a quadric, this vector, let me B, right, as the matrix of the coefficient of the quadric. I mean, just this is linear algebra. This is a good exercise for students in the second course of linear algebra, not the first course, because it's quadratic form. So, and essentially, what we have is for all m, the transpose of Vm of tau, B Vm of tau, is equal to 0. But now you can see that really you use all the trick that used in the basic course of linear algebra. But this condition you can write as also the trace of B of Vm tau transpose Vm tau is equal to 0. Okay, but now what I'm going to say? I'm going to say that then since I told you before that this space and this space are the same space, this condition that holds for all Vm holds also the same condition that the trace of B of A epsilon delta is equal to 0 for every epsilon delta that belongs to 0, 1 to the G. But now, what is this? Oh, now the epsilon delta, I consider this matrix, this is symmetric matrix, as a column vector, and I write a big matrix here. I'm sorry, but I could not find a better way to explain. Oh, sorry. First of all, let me recall. No, this I wrote is here. Yes. Okay, this is equal also to theta delta d theta epsilon minus theta epsilon d theta delta. This is a simple fact. And now I want to finish this. So I write a big matrix A, which the entries are the following. Each column is the matrix A epsilon delta. So this is what is here. A G by G symmetric matrices I write as a column vector. There are 1/2 times the G plus 1 coordinates. And here there are 2 to the G minus 1 times 2 to the G plus 1 choice of pair epsilon delta with epsilon different from delta. And this condition that B times this columns is 0 is just the condition that this matrix A has rank less than 1/2 times G plus 1. But now, how can I get the matrix A? If you remind, I defined the matrix at the beginning. M tau was just theta delta. Let me write this. Theta epsilon. Here the derivative of theta delta with respect to the tau ij. And here is just the derivative of theta epsilon with respect to the tau ij, and so on. And this is the big matrix. This is 1/2 G times the G plus 1 matrix times 2 to the G column. Now, in this matrix A, I want to give indices to the row. So M tau is just M0, M11, MGG. I want to put some emphasis on this row. And now I consider the wedge product of the first row with the second row, the first row with the third row, the first row, and so on. So now you can easily see that if you consider, let's say, M0 wedge Mij, this is just, I want to use, this matrix A, I can consider the indices along the line as I and J. And this is exactly this line. But this is linear, this is multilinear algebra. And now, the fact that this matrix has not maximal rank is equivalent to the fact that this matrix has not maximal rank. This is really an exercise of linear algebra. So whenever this has no maximal rank, this has no maximal rank, and then x tau, theta tau is reducible, is decomposable. Okay? So this is the first result that we got. And this is, according to me, is a rather nice characterization. I mean, at least the tools are really bachelor degree tools. Shortly about the second part. This I will tell you just some data, because this is still a work in progress. So I discussed T4, A epsilon delta tau. This was a modular form. Vector value, sorry, vector value. Modular form. So, as I told, if you consider A epsilon delta tau the adjoint of this, so all the minors G minus 1, G minus 1. This is still a vector value modular form. So the highest weight is G plus 1, G plus 1. This is G minus 1 times G minus 1. It's just a simple computation from representation theory. Then there is a well-known fact that if you consider the trace of A epsilon delta tau of the tau sharp, what I defined before, this is a n-1 form of Hg mod gamma, where gamma is a subgroup of finite index in gamma g. So now the problem is, for example, so in genus 6 we have many of this form. But when you try to symmetrize, they become always 0. So you cannot get any result about general type for age. I mean, you get some result about general type for subgroup of gamma g, but this is more, no, sorry, general type, not an irrationality, I mean, but this is more or less known sense. What? Yes. No, what is interesting still is, it's a work in progress, so that this form is really easy in some sense that, and sorry, this is n, so n, sorry, n was the top degree, 1/2 g times g plus 1. And I should say that 40 years ago, Freitag also gave a talk to the international conference in which he showed first example exactly on n-1 form. Now I show you the form that Freitag gave. Is this. I hope that I can write because this is really awful. So D is always the same Dij is the operator that I defined at the beginning. And then let I is equal I1 Ik, J is equal to J1 Jk. There are two multi-indexes. And then you can define delta Ij bar. This is just the determinant of Di Dj. So I choose this column, this line for the matrix of differential operator, consider the determinant. This is the differential operator that I want. And now, Freitag. This is Freitag. Several people here, they were not born yet, but okay, Giulio, okay. And so if you consider F and G to modular form or weight scalar value modular form or weight G minus 1 over 2, and you define this product, Fg is equal to the trace of B tau, D tau sharp, as before. But then I have to tell you what is B tau. So B tau is obviously a symmetric matrix. B tau Ij is equal to minus 1 at I to j. The summation for k is going from 0 to the g minus 1. Minus 1 to the k. Divide g minus 1 over k. Summation of all ei, ej, these are sign of d I j of f d I complementary j complementary of g, and here I am summing over all possible I in 1g except I, and all possible j, capital J, in 1g except. Oh, this is a mess. So it was very difficult to evaluate because one big problem, the theory of modular form, you can write modular form, but they have to prove that they're not identically equal to 0. The relation between, I have 3 minutes, okay. So, one remark. In this case, they appear differential operator of very high order. To the function f, you apply differential operator of order k. And the same here. Okay, and here is g minus 1k, so same thing. So, in this case, you have just a first order derivative with respect to tau ij. So the result that at the moment we can prove, if you consider theta epsilon to the g minus 1, this is an honest modular form of weight g minus half over 2. Theta delta to the g minus 1, this is equal to up to a constant that we can compute. Also the constant is just equal to a epsilon delta adjoint. So we had this result. Oh, now this, to prove this, you have to do some little work. Just then I conclude. Just I want to tell you that the way to cancel higher order differential operator is just because theta function, they satisfy the heat equation that I told before. So essentially, when you can play some game with the heat equation, and then you can have lots of cancellation, and all this cancellation appear here. So the idea is to have, at this point, I think we stop. And in general, I think this result can be better generalized, but this is Sarah's duties, not my duties anymore. Just to finish her PhD. So. And I think, is time? Yeah, okay. Finish.